Well, welcome back to our class on software engineering. We're going to continue our discussion in this third section as we talk about advanced topics in software engineering. Last time we talked about component-based software engineering, and now we're going to be talking about distributed software engineering. So for distributed software engineering, the four things that we'll get into is distributed systems, client-server computing, architectural patterns for distributed systems, and software as a service. And so, interesting to think about it, virtually all large computer-based systems are now distributed systems, which is a collection of independent computers that appear to the user as a single coherent system. Information processing is distributed over several computers rather than confined to a single machine, and distributed software engineering is therefore very important for enterprise computing systems. So in terms of distributed system characteristics, here's a handful of things to keep in mind. Resource sharing, this would be the sharing of hardware and software resources. Openness, the use of equipment and software from different vendors. Concurrency, concurrent processing to enhance performance. Scalability, dealing with the increased throughput by adding new resources. And fault tolerance, the ability to continue to operate after a fault has occurred. For distributed systems, there's first consider the issues. Distributed systems are more complex as systems that run on a single processor. Complexity arises because different parts of the system are independently managed in the network, and there's no single authority to change the system, so top-down control is impossible. What are the design issues? There's transparency, openness, scalability, security, quality of service, and failure management. For transparency, here's questions that you could think about as to what extent should the distributed system appear to the user as a single system. For openness, should a system be designed using a standard protocol that supports interoperability? For scalability, how can the system be constructed so that it is scalable? For security, how can usable security policies be defined and implemented? For quality of service, how should the quality of service be specified? Finally, failure management, how can system failures be detected, contained, and repaired? For transparency, ideally, users should not be aware that a system is distributed, and services should be independent of distribution characteristics. In practice, this is impossible because parts of the system are independently managed and because of the network delays. Often it is better to make users aware of distributions so that they can cope with problems. To achieve transparency, resources should be abstracted and addressed logically rather than physically. Middleware maps logical to physical resources. For openness, distributed systems are systems that are built according to generally accepted standards. Components from any supplier can be integrated into the system and can interoperate with the other system components. Openness implies that the system components can be independently developed in any programming language, and if these conform to standards, they will work with other components. Web service standards for service-oriented architectures were developed to be open standards. So in terms of scalability, the scalability of a system reflects its ability to deliver a high-quality service as demands on the system increase. And there's three things to consider: size, distribution, and maintainability. For size, it should be possible to add more resources to a system to cope with increasing numbers of users. For distribution, it should be possible to geographically disperse the components of a system without degrading its performance. Finally, manageability, it should be possible to maintain a system as it increases in size, even though the parts of the system are located in independent organizations. There is a distinction between scaling up and scaling out. Scale up is to more powerful systems, and scaling out is more systems instances. For security, when a system is distributed, the number of ways that the system may be attacked is significantly increased compared to centralized systems. If a part of the system is successfully attacked, then the attacker may be able to use that as a backdoor into other parts of the system. Difficulties in a distributed system arise because different organizations may own parts of the system. These organizations may have mutually incompatible security policies and security mechanisms. What about the types of attacks? The types of attacks that are distributed must defend it against are the following. There's interception, interruption, modification, and fabrication. For interception, this is where communication between parts of the system are intercepted by an attacker, so there is a loss of confidentiality. For interruption, this is when the system services are attacked and can't be delivered as expected. Denial of service attacks involve bombarding a node with illegitimate service requests so that it cannot deal with valid requests. For modification, this is where data or services in the system are changed by an attacker. And finally, fabrication. This is where an attacker generates information that should not exist and then uses this to gain some privilege. For quality of service offered by a distributed system reflects the system's ability to deliver its services dependably and with a response time and throughput that is acceptable to its users. Quality of service is particularly critical when the system is dealing with time-critical data such as sound or video streams. In these circumstances, if the quality of service falls below a threshold value, then the sound or video may become so degraded that it's impossible to understand. For failure management in a distributed system, it is inevitable that failures will occur, so the system has to be designed to be resilient to these failures. So, quote, you know that you have a distributed system when the crash in the system that you've never heard of stops you getting any work done. And so distributed systems should include mechanisms for discovering if a component of the system has failed, should continue to deliver as many services as possible in spite of the failure, and as far as possible, automatically recover from the failure. In terms of models of interaction, there's two types of interactions between components in a distributed system. There's procedural interaction and message-based interaction. Procedural interaction is where one computer calls on a known service offered by another computer and waits for a response. For message-based interaction, this involves the sending computer sending information about what is required to another computer. There is no necessity to wait for a response. So here's an illustration of an activity diagram of procedural interaction between a diner and a waiter. And you probably are familiar with this kind of a transaction, but putting it into this UML diagram might be useful to get some perspective on that. So here is a different way of showing that in terms of a message-based interaction between a waiter and the kitchen. And here are the kind of things that would be communicated between the two parties. And let's talk about remote procedure calls. Procedural communication in a distributed system is implemented using remote procedure calls, RPCs. In a remote procedure call, one component calls another component as if it was a local procedure or method. The middleware in the system intercepts this call and passes it to the remote component. This carries out the required computation and via the middleware returns the result to the calling component. Problem with RPCs is that the caller and the callee need to be available at the time of the communication, and they must know how to refer to each other. For message passaging, message-based interactions normally involve one component creating a message that details the services required from another component. Through the system middleware, this is sent to the receiving component. The receiver parses the message, carries out the computations, and create a message for sending components with the required result. In a message-based approach, it is not necessary for the sender and the receiver of the message to be aware of each other. They simply communicate with the middleware. So in that case, let's get into middleware. The components in a distributed system may be implemented in different programming languages and may execute on completely different types of processors. Models of data, information representation, and protocols for the communication may be different. Middleware is software that can manage these diverse parts and ensure that they can communicate and exchange data. So here is an example of middleware in a distributed system, and you can see how it's dealing with the application component and the operating system. And so it does this as translation. And we can see this in two different systems. And so literally we go from system to system, and via the operating system, the middleware translate what the application component is trying to convey back and forth between applications. In terms of middleware support, there's interaction support and there's provision of common services. For interaction support, this is where the middleware coordinates interactions between different components in the system. The middleware provides location transparency in that it isn't necessary for components to know the physical location of the other components. The provision of common services, this is where the middleware provides reusable implementations of services that may be required by several components in the distributed system. By using these communication services, components can easily interoperate and provide user services in a consistent way. Now let's talk about client-server computing. In distributed systems that are accessed over the internet are normally organized as client-server systems. In a client-server system, the user interacts with a program running on their local computer, like a web browser or mobile application. This interacts with another program running on a remote computer, for example, a web server. The remote computer provides services such as access to web pages, which are available to external clients. So here's an example of how that might look. And so you have various clients and they're accessing servers. Here we're showing 4 server processes that the various clients are accessing. So there's there needs to be a mapping of clients and servers to network computers. And so this is how that could look like. And so here is a picture of the layered architecture model for client server applications. And so there's the presentation that the client would see from their own web browser. There's the data handling, application processing, and finally the database. And so that's how it could look. Well, let's talk about those components one at a time in terms of the layers in a client server system. Presentation, this is concerned with presenting information to the user and managing all the user interactions. For data handling, this manages the data that is passed to and from the client, and there's implement checks on the data, generate web pages, etc. For application processing layer, this is concerned with the implementing the logic of the application, and so provides a required functionality to end users. And finally, the database, stores all the data and provides transaction management services, etc. Well, let's now talk about the architectural patterns for distributed systems. Widely used ways of organizing the architecture of a distributed systems are as follows. There can be a slave master architecture, a 2-tier server architecture, a multi-tier client server architecture, a distributed component architecture, and a peer-to-peer architecture. We'll go into these in more detail. So a master slave architecture is used in real-time system in which guaranteed interactions response times are required. For a 2-tier client server architecture, this is used for simple client server systems and where the system is centralized for security reasons. For multi-tier client server architectures, this is used when there is a high volume of transactions to be processed by the server. For distributed component architectures, this is used when resources from different systems and databases need to be combined, or as an implementation model for multi-tier client server systems. For peer-to-peer architecture, this is used when client exchange locally stored information and the role of the server is to introduce clients to each other. For master server architectures are commonly used in real-time systems where there may be separate processes associated with the data acquisition from the system's environment, data processing, and computation and actuator management. The master process is usually responsible for computation, coordination, and communication, and it controls the slave process. Slave processes are dedicated to specific actions such as the acquisition of data from an array of sensors. So here's a picture of a traffic management system with a slave master architecture. And so here we have the slaves are in communication with the master. We could be thinking in terms of sensor processing here. So this is a traffic flow kind of scenario. And we have a light process control process. And so here is what you're going to do for the control. And here what you do over on the left is for the sensing. For two-tier client server architectures, the system is implemented as a single logical server plus an indefinite number of clients that use that server. You can have a thin client model or a fat client model. The thin client model is where the presentation layer is implemented on the client, and all the other layers, data management, application processing, and database, are implemented on the server. For the fat client model, this is where some or all of the application processing is carried out on the client. Data management and database functions are implemented on the server. So here is comparison of the thin and fat client architecture models. For the thin client, as we talked about before, the application processing is included in the server. And for the fat client model, the presentation and application processing is included in the actual client side. For the thin client model, it's used when legacy systems are migrated to client server architectures. The legacy system acts as a server in its own right with a graphical interface implemented on the client. The major disadvantage is that it places a heavy processing load on both the server and the network. For the fat client model, more processing is delegated to the client as the application processing is locally executed. This is most suitable for client server systems where the capability of the client systems are known in advance. It is more complex than the thin client model, especially for management. New versions of the applications have to be installed on all clients as a result. So here's a picture of a fat client architecture for an ATM system. And so you have the various ATMs and they need to be communicating with the server. So there's a teleprocessing monitor and there's custom account database. All of the database and everything is out on the account server side. For thin and fat clients, there's a distinction between thin and fat client architectures that have become blurred. JavaScript allows local processing in the browser, so fat client functionality is available without software installation. Mobile apps carry out some local processing to minimize demands on the network. Auto updates of apps reduce management problems, and there are now very few thin client applications with all processing carried out on remote servers. For multi-tier client server architectures and a multi-tier client server architecture, the different layers of the system, namely presentation, data management, application processing, and database, are separate processes that may execute on different processors. This avoids problems with scalability and performance if a thin client two-tier model is chosen, or problems of the system management if a fat client model is used. Here is an illustration of a three-tier architecture for an internet banking system. And so you have the presentation on the clients, you have the web server where the account service is provisioned, and then finally you have the database server where the customer account information is at. For the use of the client server architectural patterns, there's the architecture would be a two-tier client server architecture with thin clients. So this is largely dealing with legacy system applications. There's a two-tier server architecture with fat clients and the applications where application processing is provided by off-the-shelf software, maybe it be Microsoft applications. And then there's a multi-tier client server architecture where large-scale applications, where there's hundreds or thousands of clients and applications where both the data and the applications are volatile. So those are some things to keep in mind. For distributed component architectures, there is no distinction in the distributed component architecture between clients and servers. Each distributable entity is a component that provides services to the other component and receives services from other components. component communication is through a middleware system. So here we have an illustration of a distributed component architecture. And so you have common services that feed into the middleware, and the clients with their mode that they're familiar with engage with that communication fabric that's part of the middleware. So what are the benefits of distributed component architecture? It allows a system designer to delay decisions on where and how services should be provided. It's a very open system, sorry about that. It's a very open system architecture that allows new resources to be added as required. The system is flexible and scalable, and it's possible to reconfigure the system dynamically with object migrating across the network as required. So here's an illustration of a distributed component architecture for a data mining system. And so you have the databases here on the left that you need. You have the various integrator of taking that information as was required. And that information can then be passed to a visualizer. And finally, you get either that sent to display or having an automated report generator going. And that information is then made available to clients. What are some of the disadvantages of distributed component architecture? Distributed component architectures suffer from two major disadvantages. They are more complex to design than client-server systems. Distributed component architectures are difficult for people to visualize and understand. Standardized middleware for distributed component systems have never been accepted by the community. Different vendors such as Microsoft and Sun have developed different incompatible middleware. As a result of these problems, service-oriented architectures are replacing distributed component architectures in many situations. Plus, there's peer-to-peer architectures. These are systems, decentralized systems where computations may be carried out by any node in the network. The overall system is designed to take advantage of the computational power and storage of a large number of network computers. Most P2P systems have been personal systems, but there is an increasing business use of this technology. And there's various types of peer-to-peer systems, whether it be file sharing, messaging, payment systems, databases, phone systems, and computational systems. And so those are just some various things that you might keep in mind. What are P2P architectural models? There's a logical network architecture where there's decentralized architectures, semi-centralized architectures. There are application architectures where there is a generic organization of components making up the P2P application. And finally, there are focus on network architectures. Here is an illustration of a decentralized P2P architecture. So there's just a rather interesting and flexible way that you can be talking to components. You can have a semi-centralized P2P. So there is a super peer discovery server that tries to make sure that everyone else is able to communicate properly. Okay, let's get into software as a service. So software as a service can have some use of P2P architecture. When a system is computationally intense, it is impossible to separate the processing required into a large number of independent computations. When a system primarily involves the exchange of information between individual computers on a network, and there is no need for this information to be centrally stored or managed. What are some of the security issues in P2P systems? Security concerns are the principal reasons why P2P architectures are not widely used. The lack of central management means that the malicious nodes can be set up to deliver spam and malware to other nodes in the network. P2P communication requires careful setup to protect local information, and if this is done incorrectly, then this is exposed to other peers. For software as a service, This involves hosting the software remotely and providing access to it over the internet. Software is deployed on a server, or more commonly a number of servers, and is accessed through a web browser. It is not deployed on a local PC. The software is owned and maintained by a software provider rather than organizations using the software. Users may pay for the software according to the amount of use that they make of it, or through an annual or monthly subscription. Various software providers are making more use of this. And so what are some key elements of software as a service? Software is deployed on a server, or more commonly a number of servers, and is accessible through a web browser. It is not deployed on a local PC. The software is owned and maintained by a software provider rather than the organization using the software. Users may pay for the software according to the amount of use they make of it, or through an annual or monthly subscription. Sometimes the software is free for anyone to use, but users must then agree to accept advertisements which fund the software service. For software as a service and software-oriented architecture, software as a service is a way of providing functionality on a remote server with client access through a web browser. The server maintains a user's data and state during an interaction session. Transactions are usually long transactions, for example, editing a document. For service-oriented architecture is an approach to structuring a software system as a set of separate stateless services. These may be provided by multiple providers and may be distributed. Typically, transactions are short transactions where a service is called, does something, and then returns a result. For implementation factors for software as a service, there's configurability, multi-tenacity, and scalability. For configurability, how do you configure the software for specific requirements of each organization's? For multi-tenacity, how do you present each user of the software with the impression that they are working with their own copy of the system, while at the same time making it efficient use of system resources? And scalability, how do you design the system so it can be scaled to accommodate an unpredictably large number of users? Here's an illustration of the configuration of a software system offered as a service. And so you have various users that correlate to a certain type of profile, and then that in turn gets connected to an application service. For service configuration, branding, when users from each organization are presented with an interface that reflects their own organization. Business rules and workflows, this is where each organization defines its own rules that govern the use of the service and its data. For database extension, this is where each organization defines how the generic service data model is extended to meet its specific needs. And finally, access control. This is where service customers create individual accounts for their staff and define the resources and functions that are accessible to each of their users. For multi-tenacity is a situation in which many users access the same system, and the system architecture is defined to allow the efficient sharing of system resources. It must appear to each user that they have the sole use of the system. Multi-tenacity involves designing the system so that there is an absolute separation between the system functionality and the system data. Here is just a table of a multi-tenant database. I won't get into this, but it just gives you an idea. In terms of scalability, this scalability is dealing with where you're trying to develop applications where each component is implemented as a simple stateless service that may be run on any server. You design the system using asynchronous interactions so that the application does not have to wait for the results of an interaction, such as a read request. There's a management of resources such as network and database connections as a pool, so there's no single server is likely to run out of resources. You would also want to design your database to allow fine-grained locking. That is, You do not lock out the whole records in the database when only part of a record is in use. Okay, well, let's just finish up with key points. The benefit of distributed systems are that they can be scaled to cope with increasing demand. They can continue to provide user services if part of the system fails, and they enable resources to be shared. Issues to be considered in the design of distributed services include transparency, openness, scalability, security, and quality of service and failure management. Client server systems are structured into layers where the presentation layer implementation is on the client computer. Servers provide data management, application, and database services. Client server systems may have several tiers with different layers of the system distributed to different computers. Architectural patterns for distributed systems include master-slave architectures, two-tier and multi-tier server client architectures, distributed component architectures, and peer-to-peer architectures. Distributed component systems require middleware to handle component communications to allow components to be added to and removed from the system. Peer-to-peer architectures are decentralized with no distinguished clients and servers. Computations can be distributed over many systems and in different organizations. And finally, software as a service is a way of deploying applications as thin client server systems where the client is a web browser. With that, that is the end of our lecture. Thank you very much.